Hello friends, today let's solve this range sum query again. Today let's use a new data structure, binary indexed tree. We can call it BIT. This data structure can calculate the value of function f given the range LR in big O log n time and update the value of an element in big O log n time. What is its basic idea? It's like we use some extra array, we call it a BIT, to save some partial sum. So how to understand it? For example, if we have 16 elements in this number this A array, then we use an extra BIT array to save some sums. So this 16 it covers 9 to 16, the index 9 to 16, and the BIT 8 covers the sum from index 1 to index 8. What about index 14? It actually covers the sum from index 13 to index 14. So it's just like this tree. I think it's very simple and straightforward. Like 16, we just divide it to 2. And for the left, we save it in this architecture. Hierarchical. And in the right, also save it in this hierarchical. So you can see from these trees, when the index is odd, 1, 3, 5, 7, 9, 11, 13, 15, they just save its own number in the BIT array. But for the even index, they actually save some range array. For the 2, it saves the sum from index 1 to 2. For index 4, it saves the sum from 1 to 4. And for index 6, it saves the sum from 5 to 6. For the index 8, it saves the sum from 1 to 8. So on and so forth. So let's see some concrete example. If we want to get the range sum from index 1 to 11, what item in the BIT should we extract? From this figure, we know we should extract 11 itself, and for the sum from 9 to 10, we can just call it BIT 10. And for the range sum from 1 to 8, we can just call BIT 8. So that's it. How about we want to update this value? We want to update the value 11. What values should we change? Because this BIT 12, it saves the sum from 9 to 12. So if we change one item, 11, we should also update this sum. So we should update BIT 12. The same, because 16, it covers the sum from index 9 to index 16. So if we update 11, we also need to update this BIT 16. So it gives you the intuition that if we want to get some range sum, we should go to actually backward. We get BIT 11, BIT 10, BIT 8. If we want to update a value, we should go upwards. We should update BIT 11, BIT 12, BIT 16. Okay, so this is the binary representation of this index we should update. This is when we want to get the sum. This is 8, 10, 11. We want to update something, then there will be 8, 12, 16. Okay, so how do we know this index? We will see. Before that, let's learn some basic bit manipulation. What does it mean by x and negative x? It actually means the lowest significant bit. First, let's recall how can we get negative x? We actually invert all bits in x and plus 1. So by this operation, we know that x and the negative x should only have one set bit only have one set bit. So this is 8, 0, 0, 0, 1, 0, 0, binary representation. Negative x, how do we get it? We invert all bits and plus 1. So that's the representation for negative 8. And then we end these two representations. Then we get 0, 0, 0, 1, 0, 0. It is equal to 8, but it doesn't matter. It just tells us the lowest significant bit can be get by a number and its negative number. Because from this representation, we know the lowest significant bit is here, right? The lowest significant bit is just the bit is in the rightmost, the one in the rightmost. This is the rightmost one, and that's how we get it, x and the negative x. So why it is useful? We can see two code firstly, and then we see whether it's correct. When we want to add, we want to get actually add is update. If we want to update, we should update all the elements that covers the current item. So we should plus, we should do addition. So we add low bit x. So is that correct? Yes, it is correct. Let's see the example we see before. We want to update 11. This is 11's binary representation. And what is the lowest significant bit? Is just this 0, right? 0 position. So we end this with, sorry, not end. We now already have this lowest significant bit. Then we plus it. 1, 0, 1, 1 plus 0, 0, 0, 1. So we get 0, 0, 1, 1. So 1, 1, 0 is just a 12. So this is how we get 12. We use the lowest significant bit plus this x, so we get 12. Okay, and then now we have 12. What is 12's lowest significant bit? Is this index, right? 0, 1, 2. So index 2. So that is 0, 1, 0, 0. We plus 1, 1, 0 with 0, 1, 0, 0. Then we get 0, 0, 0, 0, 1. So that's exactly 16. That's how we get this 16. So wrap up. When we have this x, how do we get the bit items cover it? That's use its x plus lowest significant bit and plus until the number equal to n. What's n? N is the size of this bit array. So same, if we want to get the sum, what's the operation we should do? It's actually minus. We use x minus low bit x. Oh well, this low bit is a function we use to get the lowest significant bit. This low bit. Okay, I just call it low bit. So x minus it. Let's see this example again. We want to get the sum. So that's well, we want to get 11, 10, 8. How to get it? This is 11. We minus low bit. Its low bit is actually 0, 0, 0, 1 because the low bit is in index 0, right? So we minus it. So that we get 1, 0, 1, 0. This is 1, 0, 1, 0. It's just a 10. Okay, continue. What is the low bit of 10? Low bit is 0010. So that we minus it again, then we get 1000. So that's how we get 8. Okay, so as you can see, when we have x, how do we know the actual subset sum? We just use x minus low bit x and continue until it reaches 0, because the boundary should be, the condition should be this x is greater than 0. Okay, final thing should be noticed that the index from 1 is not from 0. So that's the one thing should be careful. Okay, let's write the code. I think all you should understand is why we need this low bit and how to get it. And when we want to get which array covers it, we need to use plus, and it happens in the add or update operation. If you want to get the sum, then it's just try to find the low bit minus the low bit. So let's write the code. I think first we need the bit, and we also need an int array a, because this is numbers not in this class. We also need the size n. So first thing is that we initialize the bit, the size. Okay, first we should get n equal to numbers.length. Bit should be int n plus 1. A new int n. Okay, how do we initialize this bit? Firstly, every item in bit should at least cover the corresponding item in this array. So firstly, we should do I equal to 0, I less than n, I plus plus. We update I and the numbers I to this bit. Afterwards, we copy paste system array copy source array numbers, source index 0, destination array a, actually this a, destination array index 0, and size n. You should notice this order. We should update first, then we copy the value to a. Okay, how to update? Well, update. First thing we should know the delta, actually add value, should equal to the new value minus previous value, so a index. The reason that we should we will up this value to all the items covering this index. So we should get the delta first. Then we update this a to index equal to val. Okay. Then we update the bit. Do not forget to increment index by 1 because the bit is 1 index larger. So we update, so the condition is index less or equal than n. We can get the n. Okay. Then we update this bit index will increment by this add val. Then index will increment by a low bit index. Okay, let's write low bit public int low bit x. Oh, sorry. Int x will be return x and a. Okay. Okay. Sum range. We want to write a get sum because in that case you can just call it. Because currently the left to right not necessarily start from 0, so that makes us trouble. We can use right minus get sum left minus 1. Do not forget, because if you want to get 2 to 3, we should use 0 to 3 minus 0 to 1, because 2 is inclusive, so we should minus 1. Then let's write int get sum. In that case, we'll get index. Okay. What should we do? We should get a result. And while index greater than 0, result plus this dot bit index, and then index minus low bit index. Do not forget to increment this index by 1. The same reason, because bit is indexed from 1, and yeah, that's the reason. But this given index is starting from 0. Finally, return result. Okay, seems we have finished. Okay, thank you for watching. See you next time.